Welcome back to the GCSE Maths Pro YouTube channel. Today's video we're going through some specific EDEXCEL past paper questions on trigonometry, but these are some of the hardest questions that there have been in the last few years. Obviously these are mostly aimed at higher tier students, so if you're doing foundation you won't need to know half of this content, so definitely don't worry about watching this video. So we're going straight in there. Obviously the hardest part of trigonometry, you've got in general, trigonometry is SOHCAHTOA, 3D trig, which is still SOHCAHTOA but 3D. Then you've got sine and cosine rules, and then possibly the area of a triangle using the trigonometric formula. Those are kind of under the umbrella of trigonometry. The hardest trigonometry ones tend to be to do with sine, cosine rule, possibly the area one. So that's mostly what we're going to focus on today in this video, and it's more so not necessarily that the sine or cosine rule is hard, it's just that the context of the question can be quite hard. It's not as obvious that you need to use sine or cosine rule, for example. So as you can see here, from initial impressions, it's a bearings question, isn't it? There's nothing to do with trig written down. Initially you're just thinking, yeah, this is bearings. So I want to go through this because you need to know that sometimes they will combine two topics, so trig with something else, and it could be kind of disguised in there. So it's just opening up your mind to considering the fact that, yeah, okay, just because it looks like a bearings question doesn't mean I can't use other parts of my whole syllabus that I might think are helpful. So if you want to have a look at any of these questions in any more detail or their official mark scheme, then I've written down which paper they are in the corner there as well. And at the bottom on the right, you can see how many marks each question is. So question 23, this was probably the last question on the paper, if not the second to last, okay? So anything from 20 onwards, especially with EDEXCEL, is normally the last few questions. So the diagram shows the positions of three towns, Acton A, Barston B, and Chorlton C, ABC. They've then given us this information that they've also obviously drawn on to the diagram. Barston is 8 kilometres from Acton on a bearing of 37 degrees, and Chorlton is 9 kilometres from Barston on a bearing of 150 degrees. Find the bearing of Chorlton from Acton to 1 decimal place. First of all, in terms of bearings, you need to know which angle is this. So it's always written the wrong way around when it says of Chorlton from Acton. So whichever one it's from, that's the north line that you're going to go from in a clockwise direction. So because they've related Acton and Chorlton, I'm going to draw a line between them. If that's not already there, then draw that yourself. You're obviously always welcome to draw on any lines or any other kind of annotations you want onto your exam questions. I would recommend doing it in pencil just in case you need to change it in the end. So there's our line. Bearings work in a clockwise fashion from the north line. So from Acton, going clockwise from that north line, the angle that they're asking for, the bearing, is from the north line of Acton to the line that connects Acton and Chorlton. Okay, so that's just bearings, that bit there. That's nothing to do with trig. So we want to know that. Now looking at that, do you see how we obviously know the 37 degrees? We're missing this part of the angle, which, now that I've drawn the line AC, happens to be within a triangle. Now it's a scalene triangle. That's a triangle that's not right angle, it's just all the sides and angles are all different lengths, just a random kind of triangle shape. So I'm thinking triangles. What relates to triangles? Obviously trig. It's not SOHCAHTOA because there's no right angle here. So that's when I'm thinking, yeah, probably sine cosine rule, because we're looking for an angle. There's nothing to do with area, don't need to worry about that. But also bearings tend to just be angles. You can see here they've given us distances, lengths of the sides of the triangle. So that's the clue that's starting to make me think, we've got a random triangle, we've got the side lengths, we've got some angles. Could this be trig? Could this be sine and cosine rule? The other minor detail is give your answer correct to 1 decimal place. Obviously trigonometry normally comes up with decimal answers. If it was just general angles, with parallel lines, things like that, where would you get a decimal place from? You wouldn't. These are all whole numbers. So that's what's making me think, yeah, okay, that kind of adds up as well to be something to do with trig. So having a look at this triangle, with sine and cosine rule, either way you need 4 pieces of information, including the one that you're looking for. So we're looking for the angle, that's 1 piece of information. We've got 2 sides, but nothing else. So I'm missing a 4th piece of information. What could I do? They're not going to give you anything on this question that you don't need. So initially I'm thinking, right, well, could I find another side? Well, I couldn't find the side AC without knowing an angle inside the triangle, so that's not going to work. Could I therefore find an angle inside the triangle? Obviously I want this one eventually, but I can't find that directly, can I? So I've got 37, 150, how can I use those? Well, with bearings, the north lines are obviously all parallel because they're all going in the same direction towards north. So thinking about angles on parallel lines as well, before I even delve into trig. I could work out this angle because of this shape here. That is co-interior angles. They add up to 180. So let me work that out first. So 180 minus 37. Obviously this is a calculator question because you're going to end up with the decimal answer. That gives me 143. As you can see, it's not the same as 150. You don't know if that other side is the same as 150, so don't ever assume anything unless it's explicitly told to you. Then, do you see how, because I've got the other two angles, I could work out this angle inside the triangle, because all of those angles are around a point, and they add up to 360. 360 minus both of those angles will give me another angle inside the triangle, 67 degrees. Now if I come back to my triangle, what do I now have? I have two angles, including the one I want to know, and two sides. Does that work for sine or cosine rule? Well, technically yes, because there's 4 pieces of information, right? But now we need to look at it in more detail. Which of those two would it fit with? It's still a little bit harder because for cosine rule, we could work out the side AC. We couldn't work out this angle directly, could we? For sine rule, you need pairs. So for cosine rule, you need 3 sides, 1 angle. In this case, we don't have the angle, so therefore we would need all 3 sides to use cosine rule. In the case of sine rule, you need 2 pairs, 2 angles, 2 sides, and they have to be opposite each other. So for example, the 9 kilometers is opposite the angle that we want, so that is a helpful pair. That would be angle A, and let's call that side A. However, do you see how angle 67 is opposite a side that we don't know? And equally, the side that we do know, 8 kilometers, is opposite an angle we don't know. So we don't have that second pair. So there's obviously going to be another step that we need to take before I can just directly work out x. Normally these questions tend to only, or at least each step of the question, tends to only fit into either sine or cosine rule. It's quite rare that you could choose between the two. Normally it kind of fits into one or the other. In this case, we can't do sine rule because we don't have 2 pairs with only one thing missing, do we? So I'm going to have to use cosine rule, and I would use it, because I know the 67, to find out side AC. That's the only direction I can carry on with. So you'd get your formula from the formula sheet. As I normally recommend, you can scribble out the letters that they've used for the corners because they don't match what we want. We want to base it with angle A, which is the 67. So if you use a pencil, you can always rewrite the letters. So I want this to be angle A because that's how my formula is based. Therefore, side A is the opposite, which is the one I'm trying to find. This one that used to be A can now be B, so that's side B, and C can stay as it is, side C. You can obviously change the letters here to match the letters they've given you, but I find that a little bit more complicated. So we're trying to find a side, so it's already in the correct format, that's fine. And we just fill in the formula with everything you know, and type it into your calculator. And there is our answer. Now, that is not a side length, remember that is A squared, so you might want to then square root and use your A and S button to copy all of the decimals to get the most accurate answer possible. Now, because this is not our final answer, I'm going to write down a fair few of those decimals for A. So 9.419 ... and this one is in kilometers. So that's this one down here, isn't it? 9.419. Okay, now we know more information about that triangle. Let's have a look again. To find x as an angle, we need 3 other pieces of information. We obviously knew the 67 and the 2 sides weren't very helpful. However, now we actually have 2 options here. Because we've got so much information, we could either use sine rule or cosine rule. The way we could use cosine rule is we've got all 3 sides and we're just trying to find the angle, so you'd need to rearrange the cosine rule formula. Or you could use sine rule, because you see how now we've got the opposite pairs, 2 pairs, so we've got 9 kilometers and the one we want to find out. We've also got the 67 and the side we just found. So it's up to you. You could use cosine rule again to find an angle, or you could use sine rule. I'm going to use sine rule just to kind of demonstrate a different one. With sine rule, you put at the top of the fraction whatever you're looking for. So we're looking for an angle, so all the angles will go at the top. So here we've got sine x, because we don't know what the angle is, over the side 9 kilometers. Obviously, angles always go with sin, cos, or tan, right? So sine of this angle, which is 67, over this side, which I'm going to write down as 9.419, but in my calculator I'm going to copy the number so I don't miss any digits. Before we put it in the calculator though, we want to get x as our subject, so first of all I'm going to multiply across by 9. And if you've seen our previous videos with anything to do with trig, whenever you're looking for an angle, you always have to do the inverse of either sin, cos, or tan. because we don't want our answer in terms of sin x, sine x, we want to have just x. So the opposite would be sin inverse. So you see I've got my previous answer still there, so that's fine. I'm going to go straight into sin inverse and type all of this. Normal sin there because we do know the angle is 67. I'm going to put here the answer, so that will copy all of those digits. Times by 9, close the brackets. And you can see you get an answer that does seem like a reasonable angle. If you've got something less than 1, you probably haven't done the inverse correctly. So they've said 1 decimal place, so 61.6. Now, the only thing with that is don't get mixed up and think that that's the final answer. That's just x, isn't it? Remember what we were originally trying to find out. We were trying to find out this whole pink angle here. So that includes the 37. So in terms of our bearing, step 5, we need to do 37 plus 61.6, which is 98.6 to 1 decimal place. Now, I don't think they're particularly fussy about this. I don't think they would mark you down if you didn't, but technically the bearings have to have the 3 digits. So if it's 98 in that case, we would put 098.6. But I don't think they will mark you down if you forget to do that. And there's your answer. So you can see we've actually used both sine and cosine rule because it was a 5-mark question. There's quite a lot to do, wasn't there? Okay, so our next question, again, another 5 marks towards the end of the paper, if not the final question. This one, though, if you have a look at this paper here, is non-calculator. If you see paper 1, that means non-calculator. The diagram shows 3 circles, each of radius 4 centimeters. The centers of the circles are A, B, and C, such that ABC is a straight line. So they're all kind of at the same level as what we're saying. And the AB equals BC, which is obviously 4 centimeters, because that is technically that bit there, and this bit here are technically a radius each, aren't they? Work out the total area of the 2 shaded regions. So again, this doesn't really look like it's anything to do with trig, even less than the previous one, because we've got circles here and we've got area, but we could always use it to help us out. Now, as I said before, you can always annotate or draw on lines wherever you feel is helpful. I think here, because I'm kind of thinking area of a circle, that's related to area of a sector. And sectors have triangles in it, so that's kind of where I'm going. If I were to draw both of those lines, do you see how for the circle in the middle, I highlight it, this bit here is a sector, isn't it? It's quite hard to see based on how they've drawn it, but that's a sector. And if you look for the circle on the left, circle A, let's call it, if I draw these 2 lines, do you see how that's a sector as well? And if you take away the triangle, hopefully you know that this bit here is called a segment. You might be looking at that and going, yeah, I know I've got a length. So obviously that's 4, because that's the radius, isn't it? That one there is 4, because that's a radius as well. Just looking at circle A. But what is this line here? Well, look at circle B in the centre. That's the radius as well, isn't it? So we know that's 4. That makes an equilateral triangle. They're all the same sides. What are the angles in an equilateral triangle? They're all 60 degrees because it's equally split in 3, isn't it? 180 divided by 3 is 60. So if you're thinking, well, I haven't got any angles, where am I going to get angles from? It's because of the type of triangle we've got there. Each of the angles are 60, but if I just write that one there, that is 60. So my thoughts are, this is quite messy, I realise, but it is a really hard question. That's why it gets messy. If I just demonstrate on the other side, what I'm thinking is we could work out the area of circle B, pi r squared, fine. And then subtract this area and this area. It's kind of like a cutout, subtract those. That's what I'm thinking, because the shaded area is kind of a weird shape, isn't it? So I wouldn't be trying to work out directly that, I'd be trying to work out these bits. And that's why I've broken them down into different sectors and different triangles and segments, because we have formulas for those. I would say we don't know this whole angle here, so I can't work out that sector, right? So I'm going to focus on just looking at circle A. Obviously it's the same for circle C, isn't it, on the other side, but I'm just going to focus on circle A because I do have an angle here. And the same, if I draw that segment, we know that this is also 4 centimeters, and that side there is 4 centimeters, equilateral triangle, so we know that that is also 60. Okay, that's getting really messy, but you get the point. So I'm going to draw the triangle separately so you can kind of see it on its own. Oh, that's a replica of the triangle. We know that this is 60 degrees. We know that this is 4 centimeters. 4 centimeters, that's also technically 4 centimeters, isn't it? So it's equilateral. And then, drawn really badly, but that's the sector as a whole, isn't it? So I could work out the area of the whole of that sector Hopefully you know the formula, because it's not on your formula sheet, I'm pretty sure, but you just need to base it on the fact that the area of a whole circle is pi r squared times by what proportion of the circle it is. So the angle you've got over the whole angle, which is obviously 360 around a point. So here we've got pi times the radius, which is 4 squared, times by 60 over 360. Now this is a non-calculator, so remember that. Also it says give your answer in terms of pi, which is why it's non-calculator. So we've got 16 pi, and I would just simplify this fraction. So that would go to 6 over 36, which is basically 1/6. And if you were to multiply them, I'm not going to work it out as a decimal such, I would just leave it as a fraction. That's the same as 16 over 6, which would simplify to 8 over 3 pi. So that's the area of the whole sector, including that bit there. That would include all of this. As we said before, there's technically another identical one this direction, isn't there? All of that, if you were to double it. And on the other side, the same. All of this and all of that. So do you see how the only thing missing that's not shaded are these little segments here? 4 of them. Again, they will all be identical to each other, but we do need to know one of them. That's this bit here, isn't it? So that's where our trig is going to come in handy. We want to know, because we know the area of the whole sector, to find out the segment is also like a cutout. If I do the sector minus the triangle, it will leave me with the segment. So area of a triangle. Now, you're thinking half base times height. You could work out the height. It would have to be obviously the perpendicular height, this here. You could work that out by doing Pythagoras, 2 for this side and 4 there, and then doing half base times height. You could do that because it's non-calculator. The other thing is obviously you should have memorized some of the sin, cos and tan values, especially 60 degrees. They've chosen 60 degrees specifically because it's non-calculator. You could use the area of a triangle formula, which is related to trig. So on your formula sheet, it is half AB sine C. So just label your sides. Obviously the angle we've got is 60, so that's C. And then A and B are just the other two sides, doesn't really matter. So that could be angle B, angle A. So if we sub that in, we've got half 4 times 4, and then sine of the angle 60, which hopefully you would know what that is, because for your non-calculator paper you have to memorize it, don't you? So 4 times 4 first of all is 16, half of that is 8, and then sine 60 is root 3 over 2, which if we simplify, 8 over 1, that would be 8 root 3 over 2, which if you simplify again is just 4 root 3. So that's the area of the triangle. This was the area of the sector. So to find the area of the segment, this little piece here, we would subtract those two. I'm not actually going to work that out, right? That would be crazy, non-calculated. So I'm going to leave it like that. Okay, now obviously that answer seems messy. That's fine. It's just, this is one of the hardest questions, isn't it? Now, the hard bit is trying to figure out actually what were we talking about in the first place. So we want to work out the area of the whole circle B. So 4 is pi r squared, which is pi, that's the area of the circle, pi times 4 squared, which is obviously 16 pi. Then we want to subtract 4 sectors and 4 segments. So our sector is down here, remember? So number 5, total area, 16 pi minus 4 of our sectors and minus 4 of our segments. So that's technically an answer, but obviously we want to simplify it if we can, basically. But that's effectively our answer, isn't it? So let's rearrange this. 16 pi minus 4 times 8 over 3. Now they're just testing fractions as well, so you need to know that. So we multiply them, that's 32 over 3 pi, which unfortunately doesn't simplify. Again, we get another 32 over 3 pi, and then plus, because that's double negative, 16 root 3. So what does that simplify to? We want to collect all of the pi's together, so that's over 1. We need them to have all the same denominator, so they need to be the denominator of 3. That's 48 over 3, that would make 16, wouldn't it? Pi minus 32 pi minus 32, so 48 minus 64 is negative 16. So we write that again, we got negative 16 over 3 pi plus 16 root 3. That's the most simplified we can get, given that it's non-calculator, and it is in terms of pi, isn't it? You can write it like that, but for my answer I probably would just write it with a negative second, but it doesn't really matter. There's your answer. Okay, you can see why that's some of the hardest. You've got to figure out all of the shapes here, and then remember which pieces we have and which ones to subtract. Okay, our next question, we're now back to doing calculator, luckily. It's 4 marks this time, but we've still got some circles again. So the diagram shows 3 identical circles inside a rectangle. Each circle touches the other 2 circles and the sides of the rectangle as shown. They've said the radius for each circle is 24 millimeters. Work out the area of the rectangle. So, thinking about it, area of a rectangle would be length times width, or you might know it as base times height. So we need to figure out the length and the width. Now, initially, the first one is quite easy because of the top 2 triangles, you can see. We draw some lines across there. We know the radius, don't we? So we know that that's 24. The other side of it's also 24, another 24, and another 24. So you see how that goes the whole way across. So I know that that would be 4 lots of 24 would be the width of our rectangle. So that's the first thing you can do immediately. So this is 96 millimeters. Now, if you look vertically, it's not the same, is it? I know that's 24, I know that's 24, but then do you see how this overlaps a bit? There's like an overlap and we don't know by how much. So it's obviously not as simple as just doing 4 lots of the radius again, and obviously that would make a square, which they've told us it's a rectangle. So this is where it gets trickier. And it's just based on experience if you've seen questions like this before. Obviously, they're quite niche questions, but if you've seen kind of something roughly similar, where can I create other shapes? In this one, do you see where the center of each circle is? I could create a triangle there. In fact, we know that that's an equilateral triangle because, again, from the center of the circle to the circumference is the radius, 24. Same here, another radius, another radius, another radius, and so on. You get the point. So we know it's an equilateral triangle. What do we know about equilateral triangles? Obviously, apart from all the sides are the same, all the angles are the same. So we know that this would be 60 degrees, just like our previous question. 180 divided by 3 is 60. And then we know the side lengths would be 2 lots of 24. Now, what do we actually want to know? We don't really want area in this case. What we do want to know is the length of our rectangle. So if I get my line back, see how that would be a radius, and then this would be a radius. So what I want to know is the height of that triangle in the middle. Splitting an equilateral triangle in half makes it a right angle triangle, or 2 right angle triangles, right? There's a right angle, there's a right angle. So we want to know the height of the triangle. You've got 2 options here. Because we know it's 60 degrees, equilateral triangle, you could use Trig, SOHCAHTOA, or you could just use Pythagoras because we know that the base of the triangle is 24 and then the hypotenuse is 2 lots of 24. That's completely up to you, whichever you prefer, whichever you see first, whatever makes more sense to you. Because obviously we're going through trigonometry in this question, I'm just going to use Trig. So just looking at one of those triangles, let's just look at this green triangle here, we can recreate that. You can always redraw the triangle if it's getting a bit too messy on your diagram. So we know that this is 24, and we know that that is 60 degrees. So we want to find the opposite, and we've got the adjacent, we can therefore use tan, TOA. Because we're looking for the opposite, cross that out. So my actual calculation is going to be tan of the angle times by the adjacent. Now, you could write down all the decimals. For now, because it's not our final answer, I'm going to write it down in the most simplified form, which is 24 root 3 millimeters. So that's our height here, isn't it? So the last thing then is if I want to work out the length of my rectangle. Remember how I said we know that this height here is a radius, this is a radius, so that's 2 times 24 plus our answer here. So we know the width was 4 times 24, which was the 96 that we already have. And we know that the length of the rectangle is 2 times 24 plus the 24 root 3. Which just for now, because again, not final answer, I'm going to write it as 48 plus 24 root 3 millimeters. So now back to the original point of the question. We wanted to know the area of the rectangle. That's the easiest bit, isn't it? Area is length times width. So we've got 48 plus 24 root 3 times by 96, which now we will put in our calculator. And they've said correct to 3 significant figures. So now we can actually write down our answer and round it. 3 significant figures would be 8,600. And that's millimeters squared. There's your answer. So the trigonometry in this case wasn't that hard, or you could have used Pythagoras if you prefer that one, that's absolutely fine. It wasn't sine or cosine rule. However, the hardest bit is just figuring out when you've got rectangles and circles, where would a triangle be helpful? Okay, so we're back to another non-calculator question, 5 marks, question 22, probably the last question on the paper. This time we've got the diagram shows a hexagon. We've been told that the 2 halves of the hexagon are congruent parallelograms, where AB is the same as BC, which they've labelled as X, so let's label that ourselves as well. X, and then that one's also X. Technically it means these 2 down here would also be X and X as well. P is the point on AF, and Q is the point on CD, such that BP and BQ are 10 centimetres, so I would draw those lines as well. Okay, those are 10 centimetres each. And then they've said, given the angle ABC, so the whole of the angle at the top, so this is quite hard to draw, but that whole thing is 30, not just the bit in the middle, the whole thing. Prove that another way of writing cos of the angle PBQ, so the smaller angle, is writing it like this. So this is a proof question. Even though we've got x in there, we can't work out what x is. Do you see how they've still used it in their answer? We're not trying to solve for x, okay? So that's the first thing to know. We cannot work out the value of x, and we don't need to, they've not asked us to. What I'm thinking in this case is we need to kind of create some equations. We're not going to solve them as such, right? We just need to create formulas, basically equations. What 2 things in this diagram could we equate, and then in the end rearrange it to get this? We're just rearranging it to get cos PBQ as the subject, aren't we? Well, if I draw another line, P to Q, that creates a triangle in the middle, doesn't it, with the 10s and with this angle that we don't know at the top. Do you see how that would be the same length as AC? Those would be the same lengths, wouldn't they? Because we've got congruent parallelograms. So I've created 2 triangles, the top triangle, ABC, and then the bigger triangle, PBQ. It's kind of like this if I were to draw them separately. These are the 2 triangles, aren't they? And AC is the same as PQ. So because those are the same as each other, if I can write an equation that describes, or if I knew what x was, would technically calculate AC. If I can write another equation which would technically calculate PQ, and then I put them equal to each other, I should then be able to rearrange it to get this. So just look at this ABC triangle first. AC, how would you work out that side? It kind of looks like an isosceles, well, it's an isosceles, but it kind of looks like an equilateral. We can't assume that it is though, so don't make any assumptions. It's obviously an isosceles. That's fine. This is also non-calculator, right? So that's why they've chosen 30 degrees specifically. So what I'm thinking is, obviously you could split it in half, but I feel like that would be worse because then you'd get 15 degrees. And we haven't memorized values for 15 degrees, right? So that's why I wouldn't do that. I would therefore look at it as not a right angle triangle in there, just as a triangle as a whole, sine, cosine rule. I've got 2 sides, an angle, and then another side that I want to know. So that's 3 sides, 1 angle. That means cosine rule. 3 sides, 1 angle. So I'm going to use cosine rule, which is obviously in your formula sheet. If it's helpful to rearrange the letters on your triangle to match formula, then obviously feel free to do that. So cosine rule is always based on angle A, and the angle we've been given is 30 degrees. Obviously you could work it out, but let's just keep it simple. That's angle A, so that's side A. Change that to B, side C, so on. Now fill in your formula for triangle what was ABC. So that was AC squared is the same thing as x squared plus the other x squared minus 2 times x, which is x squared, times cos 30. Now, because it's non-calculator, you know that you're meant to have memorized some of the values. So that's where we would want to use that. So if I simplify this, x squared plus x squared is 2x squared minus the other 2x squared. I can't put these together because this 2x squared is attached to the cos. So I can't literally subtract those. Now cos 30 is root 3 over 2, which now you can probably see where that surd has come from. So we've got this. I'm going to simplify this fraction. 2x squared minus, that's technically over 1, isn't it? So 2 root 3 over 2 is just root 3 times x squared, isn't it? Okay, that is AC squared. Let's write that down so we don't forget. You could obviously then square root that, but I think that would just make it messier, so just leave it as AC squared, because AC squared would be the same as PQ squared, wouldn't it? So in the case of PQ squared, we can do exactly the same thing, because even though we don't know the angle PBQ, we do want it in our formula, don't we? And they've used cos as well. That's the other clue that you're going to use cosine rule. So exactly the same, but for this other triangle. PQ squared is 10 squared plus 10 squared minus 2 times 10 times the other 10. Cos, now we don't know PBQ, but they've obviously left it as PBQ, so just write it like that. Now, let's just simplify this a bit. 100 plus 100 is 200. Minus 2 times 10 is 20 times 10 is 200. That's the most simplified I can get it. Again, I can't subtract these two because the second 200 is attached to whatever cos PBQ is. So they're not like terms. Now, we know that this is the same as this. Based on our diagram, it's the same value, isn't it? So I can equate this and this to create my equation. So let's write over here 200 minus 200 cosine PBQ equals 2x squared minus root 3 x squared. So all I need to do now is rearrange it to get cos PBQ as my subject and everything else on the other side. That is it. So what I think I might do on this side, because you can also look at the answer and kind of try and figure out this backwards and then this, meet in the middle basically. They've taken out the x squared, haven't they? Do you see how I've got it effectively in its expanded format? If I were to factorize that side, I would get 2 minus root 3 and then x squared. So do you see how that's given me that format there? On the left-hand side, I think I'm going to factorize it as well, because you see how we've got 200. So 200, 1, that doesn't disappear, that's a 1, isn't it? 1 times 200 is originally 200. Minus just the cos PBQ, because I've taken the 200 out of it. So then, do you see how I can divide by 200? Because again, that's what they've done, isn't it? They've divided by 200. So I'd get 1 minus cos PBQ equals 2 minus root 3 multiplied by x over 200. Now they've written it as a coefficient, so I'm going to leave it like that. And then, this is the tricky bit, I guess, because you see how we've got positive 1, we've got negative this, and positive cos PBQ. So actually what I'm going to do is swap the cos PBQ and all of this. So one, I'm going to take away all of this, and then I'm going to add the cos PBQ. See how it's currently a negative? That makes it positive. Now I know that's written left to right, the wrong way around to what they have, but as long as all your symbols are correct, it doesn't matter if it's on the left-hand side or on the right-hand side. As long as your symbols are all correct. See how I've got matching symbols, so it's fine. And there's my answer. So because they had an equation here, we're not solving the equation, that would be impossible because we've got too many unknowns, but they've created an equation, so we just had to get two different things that we knew should equal to each other and then just rearrange from there. So again, we weren't working out what PQ or AC was, because we don't have enough information. But we used that logic of the fact that they are the same value to create two equations and put them into one. Okay, so our last one, question 19, you can see is from the June-November time 2020, because obviously June 2020 didn't happen. Paper 3, calculator paper therefore. We've got here a regular hexagon with side lengths x. So the A, B, C, D, E, F is the smaller one. So each of these side lengths for the smaller one, the white hexagon, are side length x. This hexagon is enlarged. So a regular hexagon is where all of the sides are the same and therefore all of the angles are the same. So that's good information to know as well. This hexagon is then enlarged centre F, so you can see the corner F, they've just enlarged it away from that corner, by the scale factor P to give hexagon FGHIJK, so the bigger one, the grey one. Show that the area of the shaded region in the diagram is given by 3 root 3 over 2, brackets p squared minus 1, x squared. Again, we're not going to work out what x is, we're not going to work out what p is. That would be impossible, right? We don't have enough information. We're just trying to create this kind of expression at the end and show that we can simplify it and format it to look like this. Well, so first of all, how do we work out the area of a hexagon? There's not necessarily a formula that we all know, is there? So that's why I would try and split it up. Now, it's a regular hexagon, that's key information. Do you see I can draw a triangle there and a triangle here, and then technically a cross as well. So I've got 6 identical triangles. Now, because this is a regular hexagon, all of the sides are the same, we can split it into these 6 equilateral triangles. Equilateral triangles where all the sides are the same, aren't they? So like in here that would be x, that'd be x, on the outside it's x, you get the point. They're all x as a side length. How do we work out the area of an equilateral triangle? Well, this is where I would lean towards using the area of a triangle, the trigonometric version. Area of a normal triangle would just be half base times height, but we don't know the perpendicular height. You could find an expression for that if you wanted to, by going, well, that's half x, and then using Pythagoras, but I just feel like that's a bit unnecessary for now, especially given that it's a calculator question. We might as well use the calculator. So, the area of a triangle using the trig version, which is on your formula sheet, is half AB sine C. Now, you're thinking, well, what's the angle? Well, if it's equilateral, it has to be 60, doesn't it? 60 degrees. And then AB are the two sides surrounding it. So that's half x times x, which is x squared, sine 60, which if you put in your calculator gives you root 3 over 2. And then if you multiply that by a half, that would be root 3 over 4 x squared. I'm putting that at the front because that's the coefficient, isn't it? The number. Now, to work out a shaded region, normally I think of it as a cutout. So I would work out the area of the bigger hexagon and subtract the smaller hexagon. So we need to know the area of the smaller hexagon first. That one, as we said, times by 6. We want to have 6 of those together, don't we? So times it by 6, you'd get 6 root 3 over 4, which if you simplify that in your calculator would be 3 root 3 over 2, which you can kind of see there's something there. So you're thinking, yeah, probably on the right lines, x squared. That's the area of the smaller one. Now we want to know the area of the bigger one. This is where our scale factor p comes in, if you remember that bit. I'm going to do exactly the same thing. However, what are the side lengths of the bigger hexagon? So think about it. If you've applied a scale factor, what does that normally mean? It means you multiply the side lengths by the scale factor, don't you? So for example, if we look at HI, that would be XP, wouldn't it? It would be the size of x multiplied by the scale factor. This one would be XP. All of them are XP. And if we get our triangle again, we use a different colour this time, just roughly where the centre is. That's XP, that's XP. We know that this is still 60 because it's still an equilateral triangle, just a bigger one, isn't it? So the area of that is still half AB sine C. But our AB, which are the two sides, have changed. It's now XP times XP sine 60. And then I just simplify that. So half XP times XP is x squared p squared. So you can see we're starting to get p squared in here as well. Sine 60 we know is root 3 over 2, isn't it? So and then we'll just multiply those fractions together again. So we've got another root 3 over 4 x squared p squared. Again, we want 6 of those, don't we? So then that would become the same fraction, basically, just with an extra p squared at the end. 3 root 3 over 2, x squared, p squared. That's the large one, the big one. So if we want to know the shaded area, the last thing we want to do is subtract the 2. So the big one minus the small one. That's the area of the shaded region. But do you see how they've written it differently? So now that we've got the area, we just need to format it differently. So have a look at what they've got. They've effectively factorised it by pulling out this and this. Just for some reason they put one on the left and one on the right, haven't they? Because can you see how they both have 3 root 3 over 2? They also both have x squared. So we can kind of pull those out as factors. So they pulled out 3 root 3 over 2. I'm going to put the x squared here for now. What would you get left with? Well, the first one you can see is p squared. Now this one doesn't just disappear, right? It's not 0, it's -1, because if you were to expand it, you times that by 0, it just wouldn't be there at all, would it? Which it is. So you need to times it by 1. We've got that. Obviously, they've just put the x squared at the end, so you can write that. Because they're taking, obviously, p is a constant, it's a number. All of this is just like a coefficient, so that's why I think they've put the x squared on the right-hand side at the end, because this is a number of x squared. And that's it. So those are some of the hardest EDEXCEL trigonometry questions. If you want to go back and check out the most common EDEXCEL trigonometry questions, which aren't quite as hard, go and have a look at that video now. If you also want to just recap trig in general, then I will link all of those videos down below in the description too. So if you found this video helpful, make sure to like and subscribe and leave down below any questions or comments that you might have.